Well, actually, this is the very first procedure which was modified for a slider crank. And we will see that slider is actually a crank whose fixed pivot is at infinity, okay? Of course, practically that is not possible, but mathematically, a straight slider has zero curvature. So point B has its center B0 at infinity. So this procedure is exactly the same as the first procedure we had seen for correlation of two crank angles. The only difference is B0 is at infinity, and I'm going to show how this is done, including determination of the relative pole as well, okay? So actually it is identical when you take B0 at infinity to procedure 1. So we have to determine the relative pole, and its determination is for the crank same. Draw a line Y through P12, which was A0, such that the directed line P12 prime, which is at infinity perpendicular to the slider, P12Y is negative half of the crank rotation, okay? So the only difference is P12 prime is at infinity perpendicular to the slider direction. Then we have to draw a line Z through P12 prime, which is at infinity and perpendicular to the slider direction. That passes from A0, that makes a distance from A0 negative half of the slider displacement. So if you want the slider to be traveling to the right, this is half the distance to the left, okay? So the slider displacement is negated and halved. So similar to the first procedure, intersection of these two lines yield the relative pole in position 1. So we achieved number 2 as well. Then exactly the same as procedure number 1, we are going to draw two lines through this relative pole such that the angle between these two lines is same as the angle between A0 R1 to 1, B0 at infinity. Remember, B0 was at infinity, so it's perpendicular to the slider travel. And actually, this angle was psi12 minus phi12 over 2, but if B0 is at infinity, the rotation of an infinite crank would be 0. So this is going to drop. We will have just negative phi12 over 2 should be this angle, okay? So is this. And we have to be careful about the senses of the angles, okay? For example, for this one, if you measure it from the line P12 prime, P12Y as counterclockwise, that means phi12 is clockwise, so that you take its negative so that this becomes counterclockwise, okay? It's also important. So unlike the trigonometry, it's not just the angle itself, but whether it's clockwise or counterclockwise. And if we are careful about those, then by selecting A1, that is the moving revolute joint of the crank, anywhere on L1, and if we select B1, which is the slider revolute joint anywhere on L2, then we are going to have a slider crank A0, A, B, and when you rotate the crank by 512, the slider is going to have a stroke or displacement S12 in the required directions. However, as I keep saying always, this procedure guarantees that the mechanism exists in two positions, but you have to check still whether the two positions are in the same branch of the slider crank or they may be in opposite branches. If that's the case, it's never going to move from position number 1 to 2. You have to disassemble it, okay? This is the first trouble. The second trouble, the link lengths may be inadequate or the transmission angle may be bad. But we have, like the procedure number 1, 3 free parameters to change our design, to improve it. We have selected the orientation of the first line we have drawn arbitrarily, so we can change it, or we can change where we select A1 and B1, okay? So by changing these 3 parameters, we can change the design and obtain something better. But for a slider crank, sometimes there may be more restrictions, like if the offset of the sliding axis from A0, which is A1, is dictated by the design, and this A1 may be 0 as well, that is, it should be an inline slider crank. Of course, you can't select B1 anywhere on L2, but it is imposed by this distance, so B1 would be unique. So if this is one design constraint, you lose one of the free parameters, but still you have 2 free parameters, which is good enough, still very good enough to improve the design. However, please always keep in mind, especially those of you who are attending 407 will see it, design is not a straight through process, okay? You solve one equation or you do one simulation and get the answer. No, it's not design. You have to iterate, okay? Design is an iterative process. And actually, this is the very first step of the design. You would like to achieve the motion. And of course, after achieving the motion, you have to design the links, joints, design the rest of the machine, etc. So even if you obtain a kinematically acceptable design from this, still other constraints may tell you to rework on this, okay? That's why if we have 2 or 3 free parameters, that's good. You can still change it because of aesthetics, because of material, because of safety, because of whatsoever, okay? So any questions on this? This is actually the identical procedure we have seen last week. It is procedure number 1 for correlation of crank angles, which is modified for the slider crank. Any questions? I see very, very little faces. How about the rest? Are they sleepy or sleeping? Okay, a few more. That's good. And someone is attending the class from the woods. It looks like it should be the background. Okay, now I would like to finish chapter 2 with something interesting, which is design of a centric 4-bar for dead centers. Dead center means the follower is at rest. Actually, this is a, strictly speaking, 4-position synthesis. You have 2 dead centers at 2 positions, and you require the velocity of the follower to be 0 at those positions. So that's actually a 4-position synthesis. We have 2 positions, which are the 2 ends at the dead centers, but those positions are actually, each one is 2 infinitesimally separated positions, which is order synthesis. And actually I have my 4-bar for 301, which is a crank rocker. And as you see, this rocker stops at this end, okay? It's one of the dead centers, and this is the other one. So what I'm doing is, at each of the dead centers, I'm specifying the position and the velocity, which is the derivative. So each of those dead centers are 2 infinitesimally separated positions. That's why this is mathematically 4-position synthesis, but you could also call it, if you like, 2-position synthesis. That's why I would like to cover it here. It's graphical. We will rework it for non-centric ones as well, the general case, in 4-position synthesis, in order synthesis, if time permits. So actually, this is very, very useful. For example, if you would like to design a mechanism that would run your windshield wiper, you know what the swing angle of the wiper should be, which is a design constraint. And then you have to design a crank that would rotate continuously so that you can connect it to an electric motor and then run it. That's why it's very useful. Or you may have something else that's making certain swing, which is dictated by the design, and you design a crank rocker for that. But because it's centric, crank makes 180 degrees rotation for forward stroke and 180 degrees rotation for the backward stroke. This might be an advantage if you would like to use it, for example, for a windshield wiper, because the wiper speed is more or less constant for constant electric motor speed. But if the machine is doing work in moving one side, and if it's idle going back, you would like to reduce the idle time. In that case, centric 4-bar is the worst design, because its idle time is equal to its working time, okay? So you would require a time ratio that's different than 1. It would do the forward stroke slow and backward stroke fast, okay? Which, if time permits, we will discuss later. So know the restrictions of this. While one arbitrary parameter you select is the follower length, just select it, and actually you select one position of the follower, either the folded or the extended dead center, which you like, and the swing angle is given, so the other one is determined from that. And actually, I'm going to show an example on that. So you have the folded and the extended dead centers, and one parameter is this length, if you like. Actually, this is not exactly a free parameter, as we will see in a moment, but selecting one of those is a free parameter. We will draw the line through the folded and extended dead centers, BF and BE. Then, depending on your design constraints, you can select A0 on a suitable location. This suitable location means actually anywhere on this kinematically, but of course you may have restrictions. If it's a car, you have a limited space to place this mechanism. So you select A0 on this line. That's the second arbitrary parameter. Then draw a circle whose diameter is distance BFBE, which is centered at A0, and the intersections through this line are the folded and the extended positions of the crank. So you have your centric crank rocker mechanism. So when it's B0, BE, AE, A0, the mechanism is at extended dead center. And when it's B0, BF, AF, A0, it's at the folded dead center. Well, this is something I said. This is a centric four-bar, that is time ratio is 1, and crank rotation from one dead center to the other is 180, which is not a must if it's not centric. For example, this one is not centric, and you could see that this is the extended dead center. Folded dead center is not exactly 180 degrees apart from that, okay? Slightly different. It might be very much different as well. But for this one, it's exactly 180. And let's see the application. If, of course, you have no questions, please feel free to interrupt me if you have any questions. Okay, so let's apply the procedure on GeoGebra. I have selected this length and the initial position, okay, arbitrarily. Then my swing angle, say, is 75 degrees because I'm using a windshield wiper of this type. Let's say, like this one, the old-fashioned one, which works like this. And suppose I need a 75-degree rotation. It might be 90. It might be 120, whatever. So you draw this angle and obtain the two positions of the crank. So this red one is extended and the green one is the folded. Then I apply number 2. So I draw this line, which is a dashed line, and I can select A0 anywhere on this line, depending on my design. It can be that side as well, okay? Or this side. I will select it here. That's why this side is longer, but you could select it anywhere you like, okay? Even much farther here, okay? That's not a trouble. So select A0 arbitrarily, which I did it here. And then I'm going to draw a circle whose diameter is this distance. And I'm going to show you a little trick on GeoGebra. Of course, if you're using a CAD software like NX or SolidWorks, you could do similar tricks, okay? So this is the trick in drawing that circle. Well, you have an option which says draw a circle with center and radius in GeoGebra. It's not asking the diameter, but the radius, okay? Circle, center, radius. So for the center, I click this. And for the radius, you have a window like this. What I do is I write distance B extended, comma, B folded is the diameter and divide by 2. That's all, okay? You don't need to type a number. Most probably it's something I don't know, something dot something, something, something, something. You don't need to do it, okay? You just write it, and even you may make this angle variable to change your design if you like, okay? That's the good part of parametric packages, and you can do it with CAD software as well. Okay, so this is just the trick that I do, okay? Measure this distance, and since it's the diameter divided by 2, so that's the result. That's my circle. This is the extended dead center because that was extended, and this is the folded dead center. So the final thing I would do is I would draw the mechanism and run it to see how it's working, what the transmission angles are, etc. I didn't measure the transmission angle, but you could very easily measure these two angles and see if it's suitable or not. Okay. So that's what we get. Very easy, am I right? And it's actually 4 position synthesis, not 2. So any questions up to here? Okay. This concludes the business with 2 positions, and I will start with 3 position synthesis methods, and we have just 7 minutes to our 10 minutes break. Let's have our 5 minutes, not 10 minutes break, 5 minutes break. Let's have our break right now, and after the break, I will continue, or I'll start with the 3 position synthesis. Okay, let's see where we are, what we are doing before we start 3 position synthesis. We did a review of 301, and actually we have seen some extended topics. We had seen how to design certain mechanisms for 2 positions, and actually we had 3 different classes of design problems. We dealt with 2 position of those, and we had seen an important theorem, Schall theorem, which we will keep using later. Now we will discuss in this chapter 3 position synthesis, and we will have certain derivations for 3 position synthesis, which is also applicable to 2 position synthesis as well, okay? So we may make certain go backs to 2 positions. Although it's not the derivations, those derivations are not necessary for 2 position synthesis. Those which are necessary for 3 position synthesis may be used for 2 positions as well, which we will see. Now, we will start 3 position synthesis with analytic methods, and actually you might have seen that in linkage mechanisms, design and analysis equations are mostly nonlinear unless you have gears, pulleys, etc., and velocity and acceleration, okay? Position analysis and position synthesis, the analytic equations, as we will continue seeing, are nonlinear, but the first analytic design equations are, to our surprise, linear in terms of unknowns, as we will see. So we will correlate crank angles using Freudenstein's equation, so-called, which we had derived in introduction chapter. So actually, you just do some manipulation in the input-output equation of the 4-bar. That is, you eliminate theta 1, 3, and then do certain manipulations to obtain this equation, which is known as Freudenstein's equation. And here, K1, K2, K3 are link length parameters. As you see, K1 and K2 are linear in terms of link length ratios, which are the reciprocal of crank length to the fixed link and follower length to the fixed link. Just K3 is nonlinear in terms of all link lengths, but that's not a trouble since these two are linear. Now, you could use this equation for kinematic analysis, okay? For given link lengths and say crank angle, you can determine theta 1,4. But using it in this form or just eliminating theta 1,3 from the loop closure equation has no difference, okay? So Freudenstein's equation has no advantage in kinematic analysis. What you would do is you would expand this as sine and a cosine. So you would obtain an equation in terms of sine and cosine of theta 1,4, which you could solve either using half tangent or phase angle method, which is identical as the loop closure equation when you eliminate theta 1,3. Its advantage is if you have 3 pairs of crank and follower angles. Actually, we had 2 pairs and did the design graphically in the previous chapter. Now we have 3 pairs. Then we can determine the link length parameters K1, K2, and K3 from a set of 3 linear equations and 3 unknowns, which is simple. And then we could obtain K1 and K2 very easily and then solve for K3. So that's very useful. Like this, okay? And actually, I'm going to solve an example which is from the ancient version of our 301 book. It is from the 2nd edition. Unfortunately, we don't have synthesis problems in the new editions. It says, synthesize a 4-bar mechanism that will realize the function y equals the natural logarithm of x in the interval when x is between 1 and 2. Now, actually, this problem is not exactly 3-position synthesis, but you're trying to generate a function, okay? Not at 3 discrete positions, but you would like to obtain a continuous function, okay? Of course, up to now, we know that this is not possible because this x is a continuous variable from 1 to 2, and there are infinitely many values between 1 and 2. So is y. Am I right? Of course, we don't have so many parameters to design the mechanism, so there is no way that we can realize this function with a linkage mechanism exactly, okay? But for a CAM, that's possible. Why? Because CAM has a continuous surface. Of course, there will be some restrictions when we see CAMs on the function, but at least theoretically, with a CAM surface, you can generate such a continuous function. However, for the linkages, definitely it's not possible. The same is true, for example, for Ackermann steering as well. It's some sort of a tangent function that you steer the wheels such that the inner wheel rotates more, the outer wheel rotates less, so that their normals intersect at the point where you have the center of rotation of the vehicle, okay? So you can't obtain this exactly as well. Now, how shall we do it then? Of course, we will select 3 points, which we will call the precision points. the function is exact at these 3 points, and in the remaining points, we will try to minimize the error between the function generated by the mechanism and the function that is required, okay? So this is actually a function generation, which is similar to correlation of crank angles. We will have the function satisfied exactly at the so-called precision points and try to minimize the difference between the function that's generated by the mechanism and the function that is required, okay? Well, the first thing is I will arbitrarily select how much the crank is going to rotate and the follower is going to rotate for this problem, because it's not dictated, but for certain problems, it might be dictated. So what I want is for X being 1 to 2, the crank is going to make a 90-degree rotation, and its ln is going to make a 60-degree rotation. You could make this, I don't know, 120 as well, if you like. That's fully arbitrary, okay? Unless you have other design restrictions. Okay, so I have selected these fully arbitrarily. Also, I will choose the initial positions of the cranks arbitrarily as well, because it's not dictated by any other thing, but it might be dictated, okay? So what I assume is initially both cranks are at 30 degrees like this. So this is going to become 90 at the end. This is going to become 108, 120 at the end. And in between, they will generate like, this is X on a scale like this, and this is Y on a scale like this, okay? So it's like a mechanical calculator. Definitely, we will not need a mechanical calculator, but what might happen is you may measure something and you might want to see it on a linear scale. That's very easy by electronics, okay? You may have nonlinear sensors that measure something, and then you may convert it into a linear voltage difference, for example. That's very easy, but if you don't want to use smart electronics, you would like to use simple linkages, still, these are used everywhere, okay? So don't think that I'm teaching you something absolute. This is still used. Still, for example, steering is mechanical, although it was hydraulic power assisted in the 1990s and early 20s, and right now it's electric power assisted. Still, you have the mechanical linkage. Still, such things exist. Maybe they would become obsolete later, but right now, believe me, it's still very widely used, although we have very smart electronic things as well. So what I'm going to do is I'll try to select these 3 points where I can exactly satisfy the function such that the error is minimum. And before we have very nice computational tools, Chebyshev devised something very, very simple, which works quite good. Now, Chebyshev states that this error can be minimized. This minimum is not an absolute minimum because the procedure is very simple. It's straightforward. It's even not iterative. It's called minimax. We select the precision points such that this is the, actually, if you like, displacement or the range, which is 1, which is 2 minus 1. Actually, it's the mean value, 2 minus 1 over 2. So this is the mean value. And then you just put the precision points in such three places that one is actually at the midpoint. The other two are close to the two ends, but not the end points. So those precision points are in the range, equally spaced. One is at the center and the other two are close to two ends, but not at the ends, so that the error is quite small, okay? It is not exactly minimum. And actually, after you design the mechanism, you may plot the error and manually try to relocate it a few times to have it even less. So that's very simple. If you do a real optimization, it's very computationally expensive. You can do it, no trouble. But this is something very simple. Even you can do it with a regular calculator, and that's why I like it much. So maybe at the end of your design, you say, okay, that's my mechanism. It's very good. Let me try to reduce the error. You can do optimization, but that's very quick. You can iterate very easily in your design. How it works is this, as I said. So these are the things that we have decided. This tells our precision points. Now, we need two scaling factors. One is Rx, that is how much theta 1, 2 is changing per our X value. And we had selected a crank rotation of 90 degrees, and the range of X was 2 minus 1, 1. So it is 90 degrees per value of X, okay? So 90-degree rotation of the crank corresponds to unit X. Similarly, for theta 1, 4, we have chosen it should rotate 60 degrees, and how much Y is going to change? It's ln 2 minus ln 1. So this is a number less than unity. Let me just check. Where is, I'm sorry, ln. ln 2 is 0.693 and ln 1 is 0 naturally. So that's 0 point something like 0.6 something. So if you want unit change in Y, it corresponds to 86.6 degrees approximately, okay? So that's the scale factor for Y, okay? We will need these scale factors later as well. In two cases, one is for Chebyshev spacing, the other one is for animating the mechanism and seeing the actual error. So, what happens is for I running from 1 to 3, because we can use 3 precision points. Our precision point for theta 1, 2 and theta 1, 4 are their initial values plus the scale factor to convert this linear function into the angular function, okay? So we will use these formula to convert these linear things into angles. And when I do the computation, you see this is the first precision point, which is very close to the starting point, but not exactly. It's not 1, but 1.07. Its ln is 0.06 something. And this corresponds to a crank angle of 36.03 degrees. We had selected initial as 30. So by using this formula, it corresponds to 36.03 degrees. And This corresponds to the follower angle. Oh, that's, I guess, there's a trouble in this number. It shouldn't be less than, oh, no. I'm sorry. This is 30 degrees. So I was thinking it should be 36. Yeah, it was 30. So it corresponds to 35.61 degrees. So actually, this is my pair of theta 1 to theta 1 for one pair. Okay, this is the first position where the mechanism is going to satisfy the function exactly. This is the midpoint. Because ln function is not linear, this is not the midpoint, okay? What we do is we apply Chebyshev spacing to this. It could be applied to that as well. The results would, the numbers would be different. The error might be slightly different, but that's not done, okay? So that's the midpoint for theta 1, 2. This is not, of course. And this is the end point, close to 120, it's close to 2. And this is 87 degrees, close to 90. So I'm going to solve Freudenstein's equation for these three pairs of crank angles, where y equals ln x in terms of these angles are satisfied exactly. And in between, I hope the error to be small, which will be true, okay? So this is what I have, and I have three set of equations linear in terms of the unknowns, which are the link lengths. And the solution is very easy. Just use matrix inversion, elimination, whatsoever. It's just, okay, unlike the nonlinear equations. So this yields K1, K2, and K3. And if I select A1 to be 1, A2 and A4 turns out to be two negative numbers, which I'll show you why. That's not a trouble, okay? If you say these are bare lengths, they are not, actually. I'm going to show how we can utilize it. And this is A3. A3 cannot come negative because it is from K3, which contains squares. But these can be negative. This is a bare length, but these are not. How? Actually, this is the mechanism. As you see, this is the angle you like. This is negative of it. And you can see the error here, which is actually, let's see when it starts. We don't see exactly zeros because ln of a number is an irrational number. But you see it was positive, negative, it becomes positive, increasing, decreasing, 0, negative. It will reduce, become 0 and positive, you see, and it's quite small. And you can plot this if you like, okay? It's going to make something like this. Let me show you the plot as well, because I don't have it plotted. That's a mistake maybe, but where's my pen? Yeah, here it is. So if you say that this is the error and this is the range, say this is x equals 1, this is 2. I have my 3 precision points here where I have the error 0, and yeah, I just forgot, but I think, yeah, it was starting with a negative value like this, 0 here, positive, increasing, negative, 0, and some positive. Now, you can plot this. What can you do? You may try to make all these more or less the same. That is, this is, let's say, plus delta. This is minus delta. You may try to make these two equal and all these maximas touching to those lines, okay? It won't be that way unless you're very lucky by Chebyshev spacing. But say this is less than this capital delta, just try to move. Let me switch to the laser pointer, I'm sorry. You may try to move this precision point to the right a little to increase this error. Say this is exceeding the line, then that means you have to reduce this span a little. If this is touching, don't touch this. Just move this slightly here, then this is going to increase, this is going to decrease, okay? So with a few manual trials, you can even improve this small error that Chebyshev spacing gives you, okay? Is this clear? So it's very straightforward. You don't need smart optimization routines, a lot of computational effort, etc. Is the procedure clear? Or even maybe you can say, yeah, this error is even small enough. You see, it is not, as far as I see, greater than 2%. Of course, these are discrete values, but it never goes to 2%. If you say that's okay, leave it like this. Don't do anything better than that's required for, I should say, things that you would trade. If it's for yourself or if you would like to satisfy yourself, of course, do your best, whatever you can. But if you're designing something for mass production, and if it's not very competitive, don't waste your resources, okay? And actually, I just tried to plot it very close to 3 precision points as well. They are not exact, but very, very close, as you see. This is the error. The reason it's not exactly 0 is it's not exactly the precision point. These take discrete values. And as you see, negative angle means actually I have here 36 point something degrees plus 180, okay? That's the negative link length. The length I would like to achieve is this. Just think it in terms of polar, r theta. But r can be negative, which means plus 180, okay? The same is true for this one. That's the second precision point. Again, not very exact, but the error is very small. And this is the third precision point. Okay?
Hocam ben bir şey sorabilir miyim acaba?
Definitely, please.
Şimdi x eşittir ln y demiştik ya. Y eşittir ln x demiştik ya hocam. Buradaki x ve y bu grafiklerde neyi temsil ediyor? Bu gördüğünüz.
Okay, that's a very good question. Let me return back to this animation. Now, if you put a scale from 30 degrees to 120 degrees and divide it linearly from 1 to 2, this arrow is going to point X, okay? Just think of those old needle voltmeters. Do you know them? İbreli voltmetre göreniniz var mı içinizde? Tüh, odamda yok, gösteremeyeceğim ama do you know what it is? The needle voltmeter. Or the ancient recorders have sometimes Wu meters like this when you talk, rather than the LEDs or things like that going up and down. You have all of those on the computer right now. They had a needle, a pointer. So this one, starting from here to the end, shows X, and the scale is linear. This shows its ln, which is Y. So it starts from initially 0 and goes to 0.68 something like this linearly. So let me, why not am I drawing it? Actually, that's a very good question, the use of the mechanism. Now, what you have is, let me point the starting point first. Yeah, somewhere here, I guess. Up to somewhere here. So you're going to have a scale like this. This is 1. This is 2. Let's say this is something like half. And then you can even put 0.1. Let's say 0.2, 3, 0.4, 5, 0.6, 0.7, 0.8, 0.9. Okay, so this is our X. And let me change my color. And let's see the endpoint. It should be here. It was 90 degrees. And this is, if you like, 30 degrees. So what I have is this. This is 0. This was, let me see, what was ln2, 0.693, let's say 0.7 somewhere. Okay, let's say this is 0.7. So this is 0.1, 0.2, let's say 0.3, 0.4, 0.5, 0.6. So that is our Y. Okay? Is this clear? So if you like, you have a mechanical calculator. Any other questions? And of course, thank you for this question. Actually, I think it was useful for everybody. Although my drawing is terrible, I think it's meaning what it should.
Teşekkür ederim hocam.
Estağfurullah, you are welcome. Good, someone has seen those ancient voltmeters in physics lab. But you see, this is it, okay? So you can use it for any purposes, including Ackermann steering. Any questions? Any other questions? So as you see, we can't satisfy such a continuous function with linkage mechanisms because the number of design parameters is limited. However, for CAMs, at least theoretically, you can satisfy Y equals ln X or whatever the function is, as long as it's continuous, because the surface of a CAM is a continuous surface, okay? You can shape the surface as any analytic function or as any motion you like. That's the difference between CAMs and linkages, but linkages are simple. Mostly they use lower kinematic pairs. cheaper to produce, easier to maintain, but if you want a function, it's not exact, okay? So we have to know the design alternatives and their pros and cons. What's the advantage? What is the disadvantage? Okay, any other questions? Any other comments? Okay, I think we can have our second 5 minutes break right now. Although we have 3 minutes, I can start the next topic after the break. Now, next, I'm going to show order synthesis using Freudenstein's equation. That is, rather than position, we can relate derivatives. Although it's not time derivatives, if, for example, one link is rotating at constant speed, it corresponds to velocity and acceleration synthesis, we might say. Now, this was our original Freudenstein's equation, and we can differentiate it with respect to theta 1, 2. And you can just think that there's a d theta 1, 2 by dt here. And actually, this is the good part of Leibniz notation compared to Newton's dot notation for derivatives. If, say, d theta 1, 2 by dt, which is omega, is constant, then you can think that this is just velocity approximation. So what I'm doing is I'm taking first derivative of this equation with respect to theta 1, 2. That's first order. Since we have 3 parameters, we can differentiate this once more with respect to theta 1, 2. So these are straight ahead derivatives. This is the equation I will obtain. So again, I have a set of 1, 2, 3 equations in terms of 1, 2, 3 link length parameters, which I can utilize. So Freudenstein's equation with its first and second time derivatives can be used to design a 4-bar at a single position with a specified rate and second rate. And we can determine the link lengths for those. And I'm going to show you one very common application example of this, which I believe will make the use of this order synthesis much clearer to you. So what we are going to do is actually we will select a pair of crank positions, the rate of change of theta 1, 4 with respect to theta 1, 2, and just remember, for example, this rate becomes 0 for the dead center. Remember, the follower stops and then returns back at the dead center. But you could, I'm sorry. Yeah, this is something else. I'm sorry, I just started wrongly. You could design it for a position and rate at a single position and then a second position as well, since we have 3 link length parameters. So this is actually called mixed order synthesis. So for one of the positions, you can have position and order specified and a second position as well to fulfill three equations. Okay, so that's why it's called mixed order synthesis. So that's also a possibility. So you can have a position first and second rate, or if you're not interested in the second rate, you may just specify a second position as well. That's up to you, okay? This can be used as well, but my example is actually I'm going to approximate so-called a sector gear by a 4-bar. Now, a sector gear is something like this. So it's not a full gear, and you do not have a full rotation. You don't just transmit power, but maybe for a limited range of motion, you would like to say amplify or reduce the motion. Gears, they are linear. That is, the speed ratio is constant, as you might remember from 301, which is the gear ratio for simple and compound gears. Say you may want to duplicate the rotation of this, so use this big sector gear and a smaller one meshing to this, so that when you rotate this, for example, by 60 degrees, the other shaft is going to rotate 120 degrees, but not full rotation. However, these are expensive things, especially if your machine is something simple, or maybe it's a toy, or it's something disposable. You may not want to use gears. You may want to replace it by a 4-bar. And that's a typical order approximation. You just may select the mid position of your system as the design position. And then the rate is actually the gear ratio, which is a constant. And the second rate is 0. That is, for the gear pair, when you rotate one of the gears, the change in gear ratio is 0 because that's constant, okay? So these are your design values at this point, okay? And actually, you approximate the gear at this design point. Actually, it's not approximate. In the infinitesimal neighborhood, the 4-bar and the gear will be behaving the same way. That is, it's going to have a constant speed ratio, and rate of change is 0. Of course, this is true only for the design point. As you go farther, you are going to have a difference. But if the motion is in a limited range, and if you have some tolerance that you don't want it to be exact, that's a good solution. This is a simple, cheap solution. So what do? We have the Freudenstein's equation, its first derivative and second derivative. And actually, as you might have seen, since K3 is a constant, it doesn't appear in the two rate equations. So one easy way to solve it is first solve the second and third equations for K1 and K2, and then substitute those into this and obtain K3, even hand solution or calculator. So how do we achieve this? Suppose you arbitrarily select the position of the 4-bar. This is what I have selected. The crank is at 45 degrees. The follower is 210 degrees. You may change them depending on the space you have, depending on other constraints. The speed ratio is actually negative of reciprocal of, so this is I, this is J. The radii, or you might just say it's the tooth. So this is, if you like, TJ over TI if it were the full gear, okay? which is actually given by the design, and the second rate is 0. So I'll just substitute those into my equation. These pink ones are my unknowns, and the known values are substituted. This is also known. Second rate is equal to 0, so these terms cancel out. As you see, this second equation is in K1 and K2, and the third equation is, so you can solve these two for K1, K2, substitute what you find into here, find K3. From those, you can find A2 over A1, or A1 over A2, A1 over A4, and A3, A1 over A3 from these three coefficients. Very straightforward. Okay? Or you could do it this way as well. If you want mixed order synthesis, you may design it for this position with this speed ratio, and you may want to say, for another pair of θ1 to θ14, I want the position to be satisfied exactly as well. That would be mixed order synthesis if you need it. That's another option, okay? And as you see, we have two, if you like, kinematically free parameters. You can change these as you like, and you can change the design. You can have better link lengths, better, I don't know, transmission angles, etc. Okay, but the equation is not linear in terms of these unknowns, so you can't predict what is going to happen. For example, while you're increasing this in a small range, your design may improve, but all of a sudden it may become something terrible, okay? Because these are in cosines, okay? So they are nonlinear variables, but still you can change these. These are at least kinematically free parameters, and you select them based on your design constraints. So this was another use of Freudenstein's equation. I'm going to show one final use of it if you have no question. Any questions? Okay. We can also use Freudenstein's equation for two position synthesis, but we had three parameters, remember? So that's why we were using it for three position synthesis, but we can optimize the transmission angle for the third equation. Now, this optimization, it should be said in quotes, optimization is just making the deviation of transmission angle from 90 degrees in position 1 equal to the deviation from the 90 degrees at position 2. So it's not minimizing, it's not really optimizing, okay? This is again in a minimax sense. If the two deviations are equal, and if they are acceptable, like this is 35 degrees or so, so is this, that's very good, okay? But this does not mean that it is the best solution. You can't obtain something smaller than this. So in using this word optimization, we should be a little cautious, okay? It's not the absolute minimum. It doesn't mean that it's the best value. It means only the two deviations are equal, okay? So we can use this as well. And again, this derivation is due to Professor Freudenstein. By the way, do you know who he is? Any guess? Do you know Professor Eres Söylemez? He is the author of our mechanisms book. He had his PhD with Professor Freudenstein. The origin of Professor Freudenstein is Germany, as the name says. But he moved to United States, and Germans were very, very good in graphical analysis. And Professor Freudenstein cast those geometrical things into analytical equations because the digital computers were evolving at that time, and he derived many equations, including this one, which is known by his name. And this derivation is due to him as well. Now, just recall the definition of transmission angle for any position. We had a fixed coefficient and a coefficient that depends on the crank angle. So actually, transmission angle is variable. It depends on the position. So what I'm going to do is, for position number 1, I will say the transmission angle is 90 degrees minus delta mu. And keep in mind that this delta mu can be a negative number as well. So this could be plus a magnitude as well. That's very general, okay? So it's sine of delta mu. And for the position number 2, since we want the derivation to be equal, it's 90 plus delta mu, so it's negative of this, okay? And it doesn't matter whether you have the minus here or there, as we will see in the derivation. So that means this delta mu can be a negative number as well. That is, the transmission angle may be greater than 90 degrees in position 1, and it can be less than 90 degrees in position 2 as well. That's why this is a very general derivation. Clear? I only see 2 pairs of bright eyes. We are 69 people here. How about the remaining 67? Yeah, one more pair of brilliant eyes. One more, good. You're powering me up. Thank you. Okay, so is this clear? So this can be greater than 90, this can be smaller than 90 as well. That's why it's a very general derivation. So what we have is, if I rearrange this equation slightly, what I'm doing is I'm multiplying this denominator with a 2 with this. So I have 2a3, a4 cosine mu is the same denominator, this constant term, plus 2a1, a2 cosine theta 1, 2. This is just equivalent to this expression, okay? And actually, I will use this one, which will help me, as you will see. So these two are the same equations, just rearranged. So let me have this equation. And I will try to make this equation resemble the original Freudenstein's equation. To do that, I'm going to divide the equation by this time 2a2, a4. So I'm going to have a3 over a2 cosine mu is negative this term. And this plus is not yellow, it's a little darker. You will see the reason. A4 square over A2, A4, and A1, A2, A2, A4, A2s will cancel, and one of the A4s will cancel. So if we think of the coefficients in Freudenstein's equation, actually, I can replace them with these coefficients. Okay, So that term is actually negative of K3. If you simplify this, it's K1 over K2. The reason actually A4 over A1 we have, and A2 over A1 we have. And then for this one, if you cancel A2s, it is A1 over A4, which is K2, okay? So this is how we express the transmission angle equation in terms of Freudenstein's parameters, but still I have an A3 over A2 cosine mu. Now, actually we want delta mu1, or the deviation of transmission angle from 90 at the two ends, to be equal. So I'll express this side as delta mu's. For the first position, it's going to be like this. So I'm using theta 1 to 1 for the first position, and in that case, it was positive sine mu. And for the second position, it is negative sine mu. And if I add these two equations, I'll eliminate these two. The left-hand side would be 0, and I'll have twice this, and this times this plus that, which is this, when the two equations are added. Well, this is not a very well-behaving equation. I have to solve for K3, K2, and K1. Where's K1? K3, K2, and K1. But it's not linear in terms of these three unknowns, unlike the Freudenstein's equation. However, we can solve it still. That's quite easy. The first thing is I would like to get rid of this denominator. So I'll multiply everything with K2. So here I'll have a K2 square, which is this, times this bracket. Then I'll have a minus K2, K3 for this term, which is here, and a plus 2K1 is equal to 0, which is a quadratic equation, still very easy to solve analytically. Am I right? Although not linear, it's maybe the simplest possible nonlinear equation. However, the trouble is K3 and K1 are unknowns as well, okay? They're not fixed coefficients. We are trying to look for K1, K2, and K3 using three equations. So we have the other two equations. This is the Freudenstein's equation in position 1. This is the Freudenstein's equation in position 2. So we may eliminate any two unknowns and write it in terms of the third unknown, because these two equations are linear. And you might think we could write K1 and K3 in terms of K2, but this is not what Professor Freudenstein did. I'm sure he tried each one of those, but the shortest solution is if you eliminate K1 and K2 and write everything in terms of K3 in these two equations, okay? So by using these two linear equations, we will write everything in terms of K3. So you are going to have new intermediate variables. Actually, these simplify writing many long equations. So you define intermediate parameters you define a capital delta, which is the product of cosine theta 1, 4 in position 2, cosine theta 1, 2 in position 1, cosine theta 1, 4 in position 1, cosine theta 1, 2 in position 2, which is actually the determinant of this coefficient matrix, if you like. So you define a Q1 like this. As you see, everything is known. Once you select the two positions, you can compute Q1 and delta numerically. Okay? Also, you can compute P1. So your K1 becomes Q1 plus P1 K3. Of course, you don't know K3. These are numbers, they're coefficients, but K3 is unknown. You can also compute similar to P1 and Q1, Q2 and P2. Again, these are all known, delta is known. So these are two numbers depending on the positions, so that you can determine K2 in terms of K3 as a constant plus a constant coefficient times K3. So if you substitute this back into our quadratic equation, this yields that equation in terms of K3. And again, it is quadratic in K3, okay? K3 square, you have a K3 square, a K3, and certain constant terms, like, for example, Q2 times this, which can be, again, solved analytically, no trouble. So this is the equation we have derived in K3, which is quadratic. If we factor it out, as you see, this is the coefficient of K3 squared, which you might call capital A. This is capital B, K3, and this is the constant term equal to 0. So what we have is this. These are the coefficients, which you can calculate numerically. So A, B, C are numbers, and you can obtain two solutions for K3 from this numerically, and then you can obtain K1 and K2 in terms of K3, so that you can design the 4-bar for two positions, and the deviation of the transmission angle is equal at the two end positions. But still, these two positions may be at two different branches, okay? So the mechanism may not move, okay? We have the mechanism in two positions, but they may be at two different branches. Transmission angle, yes, the deviation at two ends are equal, but we have no control on that delta mu. So it might be something like 75 degrees as well, which is not, again, acceptable. So you have to check all of those, okay? And unless you are very lucky, you won't get a usable result at the first trial. You have to iterate a little, okay? So our restrictions still apply in this, as well as in all of the previous analytic procedures that we have applied, okay? For example, if you do a bare three-position synthesis or maybe function generation, still one of the positions out of three might be on the other branch. So the mechanism may not move to that position at all unless you disassemble and reassemble it. Or, for example, if you perform a mixed order synthesis, for example, one position and one derivative and the second position may be at two different branches. It is also possible that the transmission angle might be bad. It might be possible that the link length ratios might be bad. One of the links might have 100 unit lengths, the other one is 1 or 1.5 unit length. Okay, these are unacceptable things. So although we have powerful tools, it's not the golden key or it's not the master key that opens all the doors. We may need to iterate, and definitely we have to check our kinematic design for kinematic acceptance. If it's acceptable kinematically, you can proceed, you can perform force analysis, you can start designing the links, bearings physically, etc., which is not my topic, glad. Even this much is too much. But you have to do all those checks, okay? Any questions before we have our another 5 minutes break? Is everything clear? By the way, I'm going to assign a big homework number 1 on 2 positions quite soon, and the time will be extended. It won't be just 1 week. There will be many questions. I'll assign some of those. The rest, if your time permits and you can work on those, will help you a lot to understand these topics much better. Okay? Any questions? So we have seen correlation of crank angles, which was one type of a design problem. Now we will see 3 positions of a moving plane, which is actually rigid body guidance or position of the coupler, which is something different. And we will start with the geometric treatment first. I'm just looking at you. Are you in front of your computers? I see only one person. So actually, this is our problem. We have the plane in position number 1. We have to guide it through 2 and 3. And for geometric treatment, actually, we can represent the plane by 2 homologous points, A1, B1, A2, B2, and A3, B3. Or for analytic treatment, we will use complex numbers Z1 and the orientation of the plane phi1, Z2, phi2 is nearly 0 here, and Z3 and phi3. Okay, but first we will start with the geometric treatment, then we will see analytic treatment, and then we will see how we can use that analytical treatment for 2 positions as well, which is a subclass of 3 positions. So in graphical synthesis or geometric treatment, we will use those positions, and just see this. Oops, the computer is a bit slow. Yeah. A1, A2, A3 define a circle uniquely. Am I right? And its center is A0. Or B1, B2, B3 defines a circle. Its center is unique B0. However, you don't need to select A. You may select, I don't know, C or D or whatever, okay? So any selected 3 homologous points define a circle uniquely whose center is unique as well. Clear? So straightforward. So use those 3 points to draw a circle graphically. This time center is not on a line, but it's at a point, it's unique, but definitely you can change the homologous point. So still you have 2 free parameters to do the job. Am I right? So how come we can perform 4-position synthesis, even 5-position synthesis that I have shown you at the very beginning? We will see that, okay? But that's possible. However, 3 positions geometrically, it's straightforward. Select the homologous point, find its corresponding other 2 positions. It defines a circle uniquely whose center is unique. So for designing a 4-bar, you have 2 free parameters to select. One homologous point, another 2 free parameters for the other. So still we have 4 free parameters to change our design. Okay. Why these free parameters are valuable? As I keep saying, the procedure guarantees that the linkage exists in all 3 positions, but there is no guarantee that all 3 positions are on the same branch. The mechanism may not move 1 or 2 of the other positions from the existing position, or it may have bad transmission angle. The link length ratios might be bad, etc. Okay, so this is something very valuable to improve the design. Of course, after satisfying kinematic requirements, you would also need to satisfy other constraints of the design as well, which in this course, as I keep saying, we will not discuss, but that gives you a lot of options, okay? That's why it's very valuable. Now, so it's quite simple, you see. Select the point, find its corresponding positions, and draw the circle, find the center, construct the mechanism, and try it. Okay, but let's go into this a little more detail. Now, similar to 2-position synthesis, we may take 2 positions at a time and find 3 poles, namely P12, that's the point the body rotates from position 1 to 2 around, P23, which is the pole it rotates from 2 to 3, and P13. So I will have 3 poles. And in general, this forms a pole triangle. And suppose to move from 1 to 2, this is the rotation phi 1, 2. That is, it is phi 2 minus phi 1 from our previous figure. This is phi 3 minus phi 2, and this is phi 3 minus phi 1. So this is how much it rotates from 1 to 2. This is how much it rotates from 2 to 3. And actually, this is the sum of the 2. So, well, say this is position 1, this is 2, this is 3 somehow. And these are the homologous points. You can draw, or they define actually 2 circles. And you can put your A0 and B0 to the centers of those circles. That's straightforward, okay? This was what I have told. But we also have a pole triangle like this. And we will see certain properties. there's a theorem called theorem of pole triangle, and actually the internal angles of the pole triangle is equal to the halves of the corresponding angles of rotation of the moving plane about the respective poles. That is, what I do is, okay, this is P12, this is P23, this is P13 for a hypothetical motion. It's not the motion that we had previously. So I label the side with the common index. This is 1, 2, this is 1, 3. So this is, I will call side 1. This is 1, 2, this is 2, 3. So the common index is 2. I will call this side 2. And this is 2, 3. This is 1, 3. The common index is 3. So I will call this 3. Is this clear? Labeling the pole triangle. I'm labeling the sides with the common corner indices. That's important to do it correctly. Is this okay? Any questions? I see very few people, just 4 people. Their eyes are bright, but how about the remaining 69? Do you have any questions? Is this clear how I label these? Because I'm going to define everything relative to those sides in this theorem. Is this clear? It's simple, but you know, if you miss something, everything will mess up. That's why. Okay. So what this theorem says is the internal angles of the pole triangle is equal to the halves of the corresponding angles of the rotation of the moving plane about respective poles and also the senses. That is, you rotate from 1 to 2 by an angle twice this angle, okay? So the sense is also important. This is clockwise, okay? And this angle in the triangle is half the rotation angle, including the sense. This angle from 2 to 3 is again clockwise, and this is half. And from 1 to 3 is counterclockwise, and half of this. Of course, it might be the complementary of these angles as well. Okay? So, if we draw it for our previous figure, and if we zoom to the pole triangle in GeoGebra, this is what we see. Okay, these are the angles for the previous motion we had, which was this one, okay? And that was the pole triangle. I'm zooming to this. Okay. So this is the first thing. The internal angles of the pole triangle are halves of the angles of the rotation of the plane, which might be a useful information for us. Now, the next thing is, actually, we will have so-called image poles. Now, what this is actually, if we have pole 1, 2, where is it in position 3 on the moving plane? Of course, in the fixed plane, P1, 2 has a fixed location, and it is the point around which the plane rotates from 1 to 2. But from 2 to 3 or 1 to 3, it's going to rotate about another point. Now, this is at position 3 on moving plane. Okay, so this is what we call the image pole, is location of the pole 1, 2, when you mark it on the moving plane, and when you move the plane to position 3, it is at this position. Okay, that is, let me just take a piece of paper. Suppose this is my position 1, this is my position 2, and it rotates about this point, okay? So I mark it as, I'll cheat a little. Let me do it on the desk. I'll mark it as P1, 2, okay? So from 1 to 2, it rotates about this point according to Schall theorem. Then when I move it to point 3, right now, where is it? It's P1, 2, 3 at position 3. Is this clear? So it's the location of pole 1, 2 at position 3 on the moving plane. Is this clear to everybody? It looks like a little confusing, but just keep this in mind. None of these three numbers are the same. This pole has a fixed location either in position 1 or 2 relative to the fixed or moving plane. Actually, it's the only common point in position 1 and 2. But if you move it to a third position, unless it's fixed axis rotation, it's going to become another point. And if you mark it on the moving plane in the position 3, that's its location. That's why it's called image poles. And actually, we will see why it's called image in a moment, okay? Is this clear for this one? Any doubt? Any questions? If it's okay, we have two more image poles, which is, for example, P23. So it rotates about point P23 from position 2 to 3. But if you move the body into position 1, the location of this point on the moving plane moves to this position, which is another position. And as you see, again, none of these three numbers are the same. Okay? And we also have P13. This time it moves from 1 to 3 about this point, but when it's in position 2, if you have this point marked on this, from 1 to 3, it rotates about it. But if you take it to position 2, it is where it is, okay? So these image poles are, as I said, the location of the pole on the moving plane at the position shown in the superscript. So actually, this is what I'm trying to explain. For example, location of the poles in position number 1 on the moving plane are P12 and P13. These are two fixed points about which the plane is going to rotate. That is, it's going to rotate about 1, 2 to come to position 2, or about P13 to come to position 3. But the pole for which it moves from 2 to 3 is at a different position. And actually, this also forms a pole triangle, if you like, but to distinguish it from the pole triangle P12, P23, P13, this is called an image pole triangle, and it is in position 1. Because this pole does not belong to position 1. It doesn't have an index in index 1, so it moves to position 1. Okay? Why do we call it image pole triangle, but not maybe relative or something else? That's the answer. Image poles are determined by taking the reflection of the pole with respect to the side of that triangle. That is, for example, P231 is reflection of P23 with respect to side 1 of the pole triangle. Okay, that's an important property. And that's why it's called image. Okay, you take the image or reflection of it. That's something very important that we will use. And another important thing, the image pole triangle becomes the pole triangle of the inverted motion. That is, when you fix the moving plane and move the fixed plane, maybe because you want to select the fixed pivot rather than the moving pivot, then you will work on image poles of the original motion, which would become the poles of the inverted motion. Okay? Is this clear? So image pole triangle and pole triangle just swap roles when you invert the motion. And of course, this is going to give us a very powerful tool. For example, you would like to determine the fixed pivot. Well, the location of it is not even on a line. It's fixed when you select the moving pivot. But when you invert the motion, the fixed and moving pivots will become, will exchange their roles. So you can select the fixed pivot where you like, and you will find the corresponding moving pivot for the inverted motion. That's why it's important. Okay, so how do we determine the image pole triangles? Actually, for example, here you have side 1. When you take mirror image of P23 with respect to this side, you're going to obtain P23, well, I can't use parentheses in GeoGebra nor superscript, so I'm using this a little awkward notation. So this is actually P23 in parentheses 1. So that's the location of pole 23, and it is in position 1. Similarly, you can take a mirror image of P1, what is this? P13 with respect to side 2 of the triangle, so that you can obtain the image pole triangle in position number 2 like this. So this is P132. Or you can take mirror image of P12 with respect to side 3, which is this. So you obtain P12 in position 3 like this. So that's the image pole triangle for position 3, the green one. Okay, so this red one is the pole triangle, and we have 3 image pole triangles corresponding to each position, and the pole that has no subscript at that position, for example, for this 3, is image. Okay, so we have the pole triangle and 3 image pole triangles. Is this clear up to here? Any questions on this? Any questions? Is this image pole triangle business clear how to obtain it? And what the physical meaning is? We will use it. Okay, we have another definition. This is called a ground or sometimes base point. When I say ground, don't think it's A0 or B0, okay? Now, if you have a moving point or a circle point like A, A1, A2, A3, if you take its reflection with respect to the side of the pole triangle, that is, for example, reflection of A1 with respect to side 1 of the pole triangle, or reflection of A2 with respect to side 2 of the triangle, or reflection of A3 with respect to side 3, you will obtain a single point. This is the ground point, and it's, or base point, it's called A1, 2, 3. Okay? So if you like, that's a check for finding the poles correctly, numbering the pole triangle sides correctly, etc. So it is like this, okay? This is A1, this is side 1. When you take reflection of this point with respect to that side, you will obtain this point. If you take reflection of this point with respect to that point, still it's this point, or reflection of that point with respect to that side, still it's this point. Okay? So ground or base point is an important point, as we will see in a moment. Any questions up to here? There is another geometric theorem. It says the angle formed at a pole by one adjacent side of the pole triangle and a line drawn through the base point is equal to the angle formed by the other adjacent side of the pole triangle and a line drawn through the fixed pivot. And actually, they are interchangeable. So if this is not the ground point, but the fixed pivot, this becomes the ground point, okay? So the theorem works in two sides. And let me show how this can be done. So, well, you might see also the half rotations here of those. As you see, that's 0, that's 45, this is 90, 22 and a half. Rather than 45 degrees here, it's the complementary, okay? So the outer angle is 45 degrees. This is 90 plus 45, okay? I just forgot to say it. So these half angles are like this, or just you can think that this is rotating this way, which is 270 degrees, and actually from 1 to 3, the rotation is clockwise. From this to that, it is clockwise as well, okay? 270. So this is half of it, okay? The senses fit as well. Now let's see this. As you see, this is the center of this circle, which is A0, and this is the ground point. And from this, to this side, which is side 2. And well, let me see how was the theorem. The angles are overlapping. So I think that's this, that's that. So let's check the theorem. It was saying the angle formed at a pole by one adjacent side of the pole triangle and a line drawn through a 2, 3 is equal to the angle formed by the other adjacent side. So these are the two sides, and a line drawn through a 0. So one is this angle, the other is that angle, because it says the other adjacent side. And as you see, the angles are the same. Okay. So that's another property that we will use later for graphical treatments. Now, we have another important property. We can obtain the shortest crank length when the fixed pivot is on the intersection of angle bisectors of the pole triangle. Well, you might have certain design constraints, and you may want a very short crank. Well, its size is limited. You can't go smaller than that for 3 positions, which is actually the diameter of this inscribing circle. And actually, this is the shortest crank length. You can find the corresponding point C by kinematic inversion, which I'm going to show later. But this is the shortest crank you can obtain. It is diameter of this inscribing circle of the pole triangle. Okay, so these are pieces of useful information that we can utilize. Any questions up to now? Again, it's our 5 minutes break time. Any questions? So let's start. We have another very useful theorem. 3 homologous points lie on a straight line if D1 is selected on the circumcircle of the image pole triangle. So that's another use of image pole triangle. For example, here we use the image pole triangle in position 1. So we obtain a point D1 on position number 1. And when we move it to 2 and 3, it turns out to be that these 3 positions are on a straight line, so that you can place a slider there rather than a crank, okay? Or you may draw circumcircle of image pole triangle, say position number 2. You can select any point, say F2 there. Its first and third positions will be on a straight line with position number 2. So that theorem is also very important. Any questions on this? Well, we have another important property. The slider axis, or the straight line defined by D1, D2, D3, passes through the orthocenter of the pole triangle. That is actually all three altitudes of the pole triangle intersect. So that's another important property. Now we have one final theorem which says if you want three positions of a line on the moving plane to be concurrent at a point, that is actually you have a slider which is centered to the ground by F0, and you would like to place a slider there, then you have to select that point on the circumcircle of the pole triangle. So just think this based on this slide, and actually, well, what was this? I'll just figure it out and tell you, but let me explain what this is with a figure first. This, you would like to have something like this. I don't want blue. Let me change my ink color. Okay. So this is what I mean. You want a point, fixed point, F0, like this. Write it here. And you place a slider like this, and this is your moving plane, okay, which is a straight line. So for its three positions to be concurrent here so that you can place it, this is the theorem, okay? Is this clear? So what this theorem tells, well, I think this is something I need to share with you. I'll just figure it out and tell you. So, oh, this is what we have already seen. I'm sorry, that's a duplicate slide. So actually, this concludes the graphical treatment of three position synthesis. Actually, if you think you select the homologous point, the center is definite, okay? You have these 3 points which define a circle uniquely, so its center is fixed. If you select this point, it again defines a circle passes through these points. Its center is definite. You can directly design the 4-bar. However, you should check if all 3 positions are in the same branch, the transmission angle, link lengths, blah, blah, blah. That's the visible part of it. However, these 3 positions define a pole triangle. The pole triangle has certain properties. We have the image pole triangle. We have the ground point. We have a limitation on the shortest crank. Or we may set, for example, we may choose this point in such a way that its 3 positions may be on a straight line so that you can place a slider to B2, B1, B2, say B3 is somewhere here. That's possible. Or you may have such a line that the three positions are concurrent at a point F0. So we have seen those so that you can use the slider crank inversion. These were all graphical treatments and the properties. Okay, now we will start analytic treatment, and we will derive certain equations which will be valid for 2, 3, 4, and even 5 positions. Okay, which is Erdmann and Sandor's analytic method for position synthesis. By the way, Erdmann and Sandor are other two PhD students of Professor Freudenstein, and they have great contribution to the mechanism design as well. And they have a 2-volume book. The first volume has been reprinted, but the second one, which is based on synthesis and advanced topics, is unfortunately out of print. They are older than Professor Söylemez. One of those, I can't remember, passed away just in the turn of the century. The other one, I'm not sure if he is still alive, but they're quite old. The remaining one, if he is still alive, is quite old. But one of their contribution is, as known by their name, Erdmann and Sandor's analytic method for position synthesis, which is actually, if you like, a vector equation, or you can represent it by complex numbers. Now, let me try to explain this equation, which is very, very handy and very, very useful. Suppose in the first position of your 4-bar, but keep in mind, you don't know the 4-bar, you are trying to find it, okay? What happens is you have a crank, which is represented by a vector WA or a complex number WA, okay? So just consider these as complex numbers or 2D vectors. So what I have is, from the center point, which we call A0 to A, we have a WA vector, which is this. Plus, you move from this moving pivot to a point on the moving plane, which we call ZA. So that's another vector, or it's another complex number. So from WA to ZA, you reach to point P. So these two sum up to our point P, which can be A1, no, not A1, but it's the point that represents a point, an arbitrary point on the moving plane. Then the mechanism moves to another position, which is called position J. So J is something that is different than 1. It can be 2, 3, 4, 5, as we will see, okay? So this is position number 1. This is position number J, which is different than 1. And during that motion, the point displaces by delta J, okay? Well, if you set this delta J to 0, actually it's going to be the pole between position 1 and J, but we won't set it to 0 because we're not looking for the pole. But this was what we did in chapter 2, remember? In U3, when I could see your eyes. Right now, I can't see anybody. Some photographs and that's all. I feel like I'm speaking against the wall. Okay, just one camera on, 2. Thank you. So is this clear? So I'm going to have the crank plus a vector on the moving plane, and I reach to the point P. And in position J, it displaces to PJ. So this is the displacement vector. Well, if I sum all these three vectors, actually I'm at PJ. And at PJ, the mechanism is going to have, this crank is going to rotate by an amount beta J. So beta J is the crank rotation from position 1 to jth position. So this vector becomes WA e to the I beta J. This angle is beta J. Okay? And this ZA is going to move to a position ZA e to the alpha J, where alpha J is the rotation of this plane from position 1 to position J. Okay, so this is, say, phi 1. This is phi J. Alpha J is phi J minus phi 1. It is the rotation of the moving plane. So again, I'm at point PJ. So these two quantities are equal. Is this clear? I have WA plus ZA plus delta J is point PJ. It is the same as WA e to the I beta J. This angle is beta J. Let me write it. And also, this rotates a little, am I right? This distance and that distance are not equal. So there is an angle between these two lines, which is alpha J. That's not very easy to show on this figure, but alpha J is, let me just do it this way. Alpha, yeah, that's laser pointer, I'm sorry. So alpha J is phi J minus phi 1. And if you like, you can call this angle phi 1. And this angle phi J. Or you could also measure this angle, which has a fixed difference, okay? So it's the rotation of the plane from position 1 to position J. Is this clear, this equation? This forms the basics of Erdmann and Sandor's method, and we will just rearrange this equation to put it in a more handy form so that we can analyze it. And also keep in mind, actually, we are looking for ZA and WA. We don't know them. We don't know the mechanism. To show what's going on, I have drawn this, but our purpose is to design this 4-bar. So we don't know it. We just know how this P, which is a point on the moving body, is moving, and also the amount of rotation. Okay, just remember this figure. So for analytic representation, actually P is our O, if you like. It's a representative point. And the angle of rotations are the other representative point, which, if you like, can be obtained if you know these A's, B's, etc. Okay? Is this clear? So actually we are looking for the 4 bar. Any questions? I see 4 pairs of bright eyes. How about the rest? And actually many people seems to have left. We are just 61 right now. Is this clear how we had written this equation? Good. So this was the equation we had written. And we can do some simplifications. And if you like, we can omit the subscripts for A or B, C, D, whatever, to obtain a more general equation. So I can take these two to this side. So I have W e to the I beta j minus W plus Z e to the I alpha j minus Z is equal to delta J. And this is called the dyad equation. Now, do you know what a tensor is? Any one of you working in solid mechanics or interested in solid mechanics, what is a tensor? Have you ever heard the word tensor? Yeah, someone says advanced strength, so you should know it. For example, what is stress? Is it a scalar or a vector or something else? Yeah, it is a tensor. It is a second order tensor. That's even perfect answer. Actually, vectors are first order tensors, scientifically speaking. Scalars are zeroth order. What we call tensors, like stress and strain, are actually second order tensors, and there are higher order tensors. For example, material properties of an anisotropic 3D material is a fourth order tensor, etc. It's not our business right now, but dyad in general is a specific type of a tensor, or sometimes they're called dyadic. This is not even that sort of thing. This dyad is just two vectors like this, okay? When you multiply two physical vectors without any sign in between, this forms a tensor, which is sometimes called a dyad or dyadic. But there are other multiplications of vectors as well. Remember the dot product, which results a scalar, the cross product, which results another vector. But if you just put two vectors together without any sign in between, it forms a tensor, which is called dyad. Now, this dyad is not that dyad, okay? This dyad is, you have one vector, which is W, another vector, which is Z, okay? So you don't do multiplication, but if you like, you add it, but it's known as a dyad. So be careful, we are not working with tensors. So we can still represent it with complex numbers. So that's the general form of our dyad equation, and J may be 2, J may be 2, 3, J may be 2, 3, 4, J may be 2, 3, 4, 5. We will see that it's not possible to make J 2, 3, 4, 5, 6 because we will have more equations than the available number of unknowns so that we can't solve it. But this derivation is very important, and actually it will form the basis of our continuing analytic discussion. We will also continue to see the graphical positions. Now, we can represent delta J as Rj minus R1. These are complex numbers as well, representing planar vectors. So it's the displacement of point P from the initial position in J. And as I said, alpha J is the rotation of the moving plane in position J. Beta J is the rotation of our unknown crank. We are looking for the crank, and we don't know how much it's going to rotate from position 1 to J, but alphas are known. So this is, again, my equation. You might see R1 as the position of the selected point in 1, and Rj is that position. Just don't think it's just same vector rotating, okay? This is making a general plane motion, so it may get shorter or longer in addition to a rotation. So for 3 positions of a plane, which can analytically be represented like this, R1 is position of a representative point, which might be the origin of your moving coordinate system, if you like, and the angular orientation at that point. So actually this has 2 variables in it. This is 1. To position 2 and to position 3. What do we have? We can write the general dyad equation like this. Okay? So we can determine delta 2, delta 3 by delta 2 is R2 minus R1 in complex numbers. Delta 3 is R3 minus R1. And alpha 2 is phi 2 minus phi 1. Alpha 3 is phi 3 minus phi 1. They are known. What is not known? Actually, I have 2 complex equations, which means 4 scalar equations, and I have 6 scalar unknowns. W and Z are 2 complex unknowns. This corresponds to the position of the unknown crank in the first position, and Z corresponds to from moving pivot, which is A1 to P1. These are unknowns. So I have 4 unknowns for these 2, 4 scalar unknowns, because they are complex, and the 2 corresponding unknown crank rotations. Okay? Now, the good thing is these 2 equations are linear in those 2 vectors, but it's nonlinear in beta 2 and beta 3. However, I have 2 complex equations, or corresponding to 4 scalar equations, and 6 unknowns. So I can solve these equations if I assume 2 of the scalar unknowns, or I have 2 free parameters. So what I would do, like Nasrettin Hoca losing his ring in the shed and looking for it in the light because the shed is dark. Do you know that joke? Nasrettin Hoca çayırda yüzüğünü arıyormuş. Komşusu da sormuş, hoca nerelere düştüğünü biliyor musun? Ben de yardım edeyim. O da ahırda kaybettim demiş. O zaman niye ahırda aramıyorsun? Çünkü orası aydınlık. So what I'm doing is, I will not try to solve it in terms of nonlinear unknowns. I will take them as my free parameters, okay? I'll set beta 2 to 30 degrees, beta 3 to, I don't know, 60 degrees, and try to solve the corresponding W and Z, and find a set of vectors. If I just change these, I will find another set. So I'll just trace it, okay? So I'll just use these nonlinear variables as free parameters to obtain different solutions. And what happens I knew the position of the representative point. Every negative Z1 from P gives me a candidate for A1, which can move to A2 and A3. And from that A1, every negative W, which is another complex number, locates a candidate for A0. So, for example, you can set a crank rotation of 30 degrees and a crank rotation of 45 degrees from position 1 to 2 and 1 to 3, and find these. If you don't like it, change it and obtain the mechanism. Of course, I can imagine what you're thinking. Graphical is very simple, you say. I'm going to pick a point. Its 3 positions define a circle. I can find the center of the circle, use it. Yes, you're right. But why this is important is when you have the 4th position, can you select any point and those 4 points lie on a circle? The answer is no. So this derivation will be very useful in 4 and 5 position synthesis, as we will see later, but it's applicable to 3 positions and also even 2 positions. Just omit this. What you need is W and Z, 4 unknowns, but just 2 scalar equations. You can select beta 2 and still everything is free. You can even select one of the free parameters in those. So that's why this is very general, although it might not be very handy in 2 or 3 positions. It's easier to analyze the properties of this Erdmann and Sandor's general form. And oh, time is up. Wow. Well, actually, this is a good point to stop. Next week, we can just start with a short review and then continue. I'll just let you know what we will do next week.